So what you got? Amers. 80. Copy. Bloop. All right, says assume all the variables are positive, expand using your property of logs, okay. So probably the obvious thing to do to start for 80 would be to do the product property since there's no quotients. Good with that. And clearly on the second log, I have a power property as well that I can do.
So that would only apply to the X value then? So like power, you wouldn't put it for 100,000. I just want to make sure.
Yeah.
Okay.
Yeah. However, if I look at 100,000, I notice that that is really 10 to the third. And log is base 10, right? So log base 10 would cancel with exponent base 10, leaving just the 3 from the exponent. So that's probably our best answer there. Sneaky!
Oh, you have log to base of whatever, then you cancel it out with the just a
Exponent base 10 and log base 10 cancel each other out.
right.
You got it.
So would you mark us wrong if we didn't do that?
Yep.
Okay.
Because your answer does is not fully expanded.
Okay, gotcha.
Teagues. Sure. And by wrong, Paul, I would not full credit.
Right. Yeah.
Right. Like you would have done parts of it right. All right. It says the half-life of a certain radioactive substance is 14 days. Suppose there are 6.6 grams present initially. Part A, express the remaining, the amount of substance remaining as a function of time t. So remember, we would write P of t equals the initial times 1 plus negative 50 over 100. How do I know the R is negative 50? Half-life, right? Half-life. Half. And it's negative because it's decay, right? Everybody's cool?
Yeah, is radioactive the only type that you use a negative for? Like,
No, if any decay.
Okay, so any decay.
Like if the population was decreasing,
Okay, right.
blah, 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 it's a decay by some percentage, then it would be negative
So
also.
radioactive and decay, you automatically have a negative.
Yeah. And then,
Wait, so then if it's normal,
hold on, we're still got some more to do on this. Can I finish and then,
Yes.
okay, that's okay. So it says the half-life is 14 days, and it says a function of time t, so I'm going to make t in days. How much of a half-life do I finish in 1 day? Takes 14 to get a full half-life. How much do I get done in 1 day?
1/4, so T over 14.
Yeah, 1/14. So I'll make that t over 14. Good. Okay. Teagues.
oh yeah, so then if the question was asked, it's like decreasing at a rate of like 0.59%, and you just do like negative.
Correct. Yes, that's exactly right. Like if you were up here in 17 through 28 or whatever. Yeah. Part B says, when will there be less than 1 gram remaining? So basically, I'm just going to be solving that equation there, where I've plugged 1 in for P of t. Does it matter that it says less than? Really just means any time after that would also be true. So I'd say after blah, blah, blah days or whatever.
Oh, so if you said 1,000,000 days, you're right.
No, I would have to say, because it says when will there be less than, so you need to cover all of them, not just one instance when there's less than. Although 1 million is probably going to be true that it'll be less than 1 gram after that long, but it would not be like completely correct because it's asking basically for all the days.
Right, I see.
You know what I mean? Yeah. So let's think about this. So we start with 6.6. Half of that's 3.3. Half of that's like 1.6-ish. And then half of that is going to be less than 1, right? So how many half-lives did we do there? 4, I think. Everybody agree?
You kind of lost.
Or 4 or 5, it doesn't really matter. Either way, that'll be less than 100 days, right? So I'm going to just use 100 days there because it's a nice round number for my winder. My lower bound is 0 since it's a decay. You can't get less than 0 amount of stuff.
Right.
My upper bound would be 6.6, but I'm going to start at 10 just because it's a round number. And I don't like doing like weirdo 6.6s or whatever. I'm just, give me good old fashioned normal looking tick mark. So there's my 1 gram, there's my decay curve, second trace, intersect command, enter, enter, enter. So after about 38.11 days, and here the after would be really important, right? Because it says, when will it be less than 1 gram? So it's like all the day, all the times after that. I probably wouldn't give you full credit if you wrote 38.11 days and didn't say after, because the question's described as an inequality there. You know what I mean? I know that feels picky, but it's like, kind of matters. If you said t greater than 38.11 days, I'd be okay with that. Or greater than or equal to. Mackenzie, sorry, I almost wrong-em'd you. 92? Okay. So here we're asked to condense these things, right? So the first thing I'm going to do is the power properties. Notice that the power property, I'm using an extra set of parentheses because that power needs to apply to everything inside the logarithm. So exponent of an exponent we multiply. So let me simplify those. So far, so good. Product prop is next. So everything is just multiplied together. If I combine like terms, I can combine the y to the third and the y to the second by adding the exponents since the bases are being multiplied. And that should be my final answer. Does that feel okay, Mac? Oh, boogers. Cool. Who's next? Amers.
Number 14, please.
Sure. Nope, that's on the previous page. Okay, if the population growth is exponential, which city and which year will the population reach 1 million people first? Of course, you picked the one where I had to have done questions 11 and 12 before I could do 14. It's okay. So I'm going to just do that, the part for 11 and 12 real quick on the calculator. Because I've done them a couple of times. already. So 656, 562 divided by 465, 622. Gonna store that as A for Austin. It's a city, not a person, but that's cool too.
Nice city name.
Sure. Is that like your middle name or something? Are you secretly just complimenting yourself?
My middle name is Gene Ernest. I have two
Is what?
Gene Ernest.
Oh, I thought you said Genarius. I'm like, whoa, that's a cool sounding name.
Yeah, that's a mouthful. I have two middle names.
You sound like a, like a Greek hero or something. All right. So, Amy, what I would do to do number 14, I would do both of my models. So my model for Austin, and then my model for Columbus, along with the 1 million line. And I think I'm gonna do the fat line for Columbus so I can tell the difference between the two. So I can answer the which one. 0 to 100 is probably fine. My smallest population initially of the two is the 465, so I'll make my y-min at 400,000. It's asking us about 1 million people. I don't like to do exactly 1 million because I want to be able to see that line a little bit more clearly. So I'll do like 1.25 mil. And go up by 100,000s or something. All right, let's hit graph. Here's my Austin line. There's my Columbus line. And there's my 1 million line. So Austin wins. They get to 1 million first. Second, trace, intersect, command. So first curve matters here. I notice up at the top it's telling me it's on Y1 right now. That was Austin, so I'll press enter there. Now it says it's on Y2. That was the equation for Columbus. I don't want that one, so I'm going to press the down and move it on to Y3, which was the 1 million line. Press enter and enter again. So there it is at 22.24 years. Feel okay there?
Yep.
Sure thing. Consequently, what we have here, we could have also done question 13 because we're looking for that intersection where they have the same population. So that's nice that I have the same graph, or could also get the same information from that picture. All righty, who's next, if anybody?
Could you just go over log again real quick? Like, so.
It's kind of like a
I know,
whole
that was
section.
very broad. What I mean is, you have log, like log base equals x. The
Log
4 equals
log 4 of what?
4 of 5.
Okay.
And then equals none. So the way we put that without a log, it would be 4 to the x power equals 5. Is that it?
Yes, that is the equivalent exponential equation.
Okay. And now, what would it look like if you didn't have anything in the parentheses? Like,
Nonsense?
It doesn't, you can't do that.
Right, that'd be like having, what is square root of x, or square root equals x mean?
Okay, gotcha.
It'd be like, you're missing the number under the square root symbol?
Okay.
Or it'd be like 3 plus what is equal to x? Or
Right.
3 plus nothing is equal, it's like, well, that's garbage. You can't do 3 plus,
I thought I saw a problem with log base like something equals something else. I was like really confused.
oh.
Maybe it was just me.
Yeah, you might have just
Probably.
misread something, or it might have been a typo or something. Who
Yeah.
knows?
Okay, then I'm good.
Okay, no problem. Alrighty. Today we're gonna start up section 15.4, and then whatever we don't, or we'll stop section 15.4 by 2:25 at the latest to do the homework quiz. We'll probably finish before then, but if for whatever reason I get sidetracked and keep on talking, feel free to interrupt me at 2:25 and be like, yo, Mr. Kulik, you need to be done now, and I will certainly drop what I'm doing. I don't think that'll be an issue. I think I was like a good 10 minutes ahead of schedule last time I did this. All right. In section 15.4, we're going to be talking about solving exponential and logarithmic equations. To this point, our solving method was graphing them on my calculator. Today, we're going to learn how to do this algebraically. So no graphs necessary, which is nice. The property that we're going to be relying on is this one-to-one property. So this says for an exponential function, f of x equals b to the x, if b to the x is equal to b to the y, then x has to equal y, which should come as no shock, right? If I said 2 to the third is equal to 2 to the x, x just has to be 3, right? Pretty common sensey, and we can say the same thing then about log Everybody cool with that notion? So sometimes it's really convenient to use this definition directly. Other times we'll kind of interpret this a little bit differently. All right. Let's say we have the equation 12 times 3 over 2 to the x over 5 equals 27. First thing we want to do is divide by 12. Very good. My goal is to get the exponential piece by itself. So certainly I can divide both sides by 12. Could I have multiplied the 12 into the 3 over 2? Would that be okay also?
No.
No, very good. Why not?
Just in the parentheses, you have to do x to the over.
Because the exponents are different.
Yes, that's it.
That's what it comes down to. Yes.
That's what I was saying.
If the bases are different, the exponents need to be the same in order to multiply them together. The 12 has exponent 1, the 3 over 2 has exponent x over 5. Different exponents. If they both had the same base, you could multiply them together by adding the exponents and keeping the base the same.
Right,
But if they're both of them are different, there's nothing we can do with that.
okay. So then we do log
Well,
3 over 2, right?
that is one way of doing it, sure. But before we do it that way, what we're going to try to do is use this property.
Right.
So on my left-hand side, I have a b to the x. What I need to do now is to write the right-hand side as that same b to the y. So how can I rewrite 9 over 4 as a power of 3 over 2? What?
Divide by.
Squared, right? 3 over 2 squared is 9 over 4. Because 9 squared is, or 3 squared is 9 and 2 squared is 4. Easy. So we can use that one-to-one property to say then that the exponents are equal and multiply both sides by 5 to get 10. Everybody okay there?
Yeah.
Now, alternatively, at this step, Paul had suggested to take log base 3 over 2 to both sides. That is also an acceptable method. And oftentimes I don't know if I want to say easier, but the more obvious route, sometimes it's quite difficult to rewrite. In this case, like the 9 over 4 is something with the base 3 over 2.
Right.
Sometimes the exponent there could be very difficult to find on your own. If we do it this way, we don't have to worry about finding that.
You just plug it into the calculator.
Yeah, we will be using our calculator in just a moment. So we multiply both sides by 5 to get the x by itself. And now it's calculator time. So 5 times, and then I press log or math, and then choose the log base command from the very bottom. And that allows me to type it in just like it looks on my sheet of paper. And I get 10, exactly the same as I did the other way. Feel okay doing that?
So it's like you can check your answer.
It's just the same, it's doing the same thing. It's equivalent work. It's actually doing equivalent thing because figuring out what this 2 is exactly this question, right?
Yeah.
We're just using the calculator to do that, to answer that part of our question. Let's do another.
Divide by 14.
Divide by 14. Good. Good.
So,
I turned into a billy goat there for a moment. Okay. So if I want to use the one-to-one method, I would have to rewrite 9 as a base 1/3 number. So 1/3, what power of 1/3 is equal to 9?
negative square, like taking negative square root, like you square root and take the inverse. Yes, that.
-2
Oh.
is what you mean.
Right.
Because 3 squared is 9, and then we'll need to flip it to make the negative. Or because the negative exponent flips it.
Wait, wouldn't it be 1 over negative 1 over 2?
That would be a square root. The square root of 1/3 is not 9.
Oh, we're okay.
This is why the other method of using a log is often easier, because this question can be kind of tricky. And sometimes not even have like a rational number answer. Like it could be like a cuckoo crazy decimal.
No, I get it. I was thinking if you did minus 1/2 to the 9, then you would get 1 over 3.
-1/2 to the 9th
No,
would be
no.
1 over 100 or 1024.
No, like if you're 5,
Or -1 over 1024.
wait, with the base 9?
You said 1/2 to the 9th.
No, I meant 9 to the negative 1/2.
9 to the -1/2 would give you 1/3.
That's what I was thinking, yeah.
Ah, I see.
Because like I was saying, oh, if you did that, then I was just reverse.
You had it reversed. Yeah.
That was 1.
Yeah. Don't moonwalk. Yeah.
Some people do it.
Okay, so you can do it that way. Alternatively, we could use a logarithm. Which log would I want to use? Log base?
It's 1/3.
Good. Are we all okay with y log base 1/3?
So it cancels out nice and pretty.
Yeah, it matches the exponent base. Did you have to use that one? Don't have to, but like the arithmetic gets kind of crummy if you don't. So like, why wouldn't you just do it the easiest way possible? And again, if I type this into my calculator, I get the exact same thing. Shocking, right? How we doing? Okay so far? All right, let's do one more of these exponential equations, and then we'll move on and talk about some logarithmic guys. Oh, boys, you take a look at this, and there's probably, 2 or 3 things that are like, oh, I'm not really sure what to do with this. What 2 or 3 things do you notice are distinctly different about this problem than the previous ones?
The 4 is under.
So we have a fraction.
Yeah, we have a fraction.
Yep. What else?
Negative.
There's an
Negative exponent. Good. What else?
X in the exponent.
Well, the x was in the exponent in the previous
Oh,
ones.
shoot, never mind.
But we have x's in 2 different places, right? Those are the 3 things that I would say that are distinctly different about that. So let's kind of try to knock these out one at a time. Let's start by getting rid of the fraction part. How could I do that?
So you could do. I was thinking you would split the fraction actually. You could multiply it by 4. Okay.
Multiply both sides by 4.
See where my head went is you would split it to 3/4 plus 3/4, and then could you use a property between the two? Let's say no.
Not if they're added.
Oh, that's right.
All right. Can I add 3 to the x and 3 to the negative x?
No,
No, why not?
because they're different.
They're not like terms. To add 2 things, they must be
Like term.
identical, right? All right. Next, let's worry about this negative exponent. How do we get rid of the negative exponent? You could make it 1/3 to the x, but what's that doing? In doing that, we get another fraction, right? Let's do it so we don't get a fraction. Here's the trick. I'm going to multiply both sides by 3 to the x. Wait, why would you want to do that? Well, I'm going to get then 3 to the x times 3 to the x plus 3 to the x times 3 to the negative x equals 8 times 3 to the x. How do I simplify 3 to the x times 3 to the x? The bases are the same, so we can add the exponents.
3 to 2x.
Yep. And then we'll get 3 to the x minus x. What's that going to be?
Plus 3 to 0.
0. And what's 3 to the 0?
1.
1. All right. Well, there. Goodbye, negative exponent. I'm going to now just move everything onto one side. How many terms do you see in this equation?
4.
I would say 3.
Oh.
Right? We have 3 things that are added or subtracted. The stuff in between the addition and subtraction are the terms,
Oh, yeah.
Right.
I was thinking addition.
not numbers. Yep. Okay. What kind of equation have we solved before that has 3 terms like that?
Quadratic.
Quadratic. Guess what?
Quadratic.
This is in the quadratic form.
Oh, fun.
What? I don't see it, Mr. Kulik. Well, let me remind you.
Oh, I see it.
We have this property of exponents. The exponent of an exponent multiplies. So I can take 3 to the 2x and think about it as 3 to the x squared. Now it should be much more obvious. If it's still not obvious, let's just like make a little simple substitution. And now it is expressly quadratic. Cool! How do we solve a quadratic equation?
Quadratic formula.
Or what's the other method?
That's the test. Oh,
Factoring,
factoring. Oh.
right? Now, typically factoring is easiest when the leading coefficient is 1. So that's the case we have here. Let's check to see if we can factor, because if we can, it's usually easier than the quadratic formula.
Right.
So we need to find two numbers that multiply to give us 1 and add to give us -8. Do you know two rational numbers that do that? I don't either. So what should we do?
Make up a number.
No. Quadratic formula. The one thing that you wanted to do originally.
Yes.
So -b plus or minus square root b squared minus 4ac
Over A.
over 2 times a. All right. So that's 64 minus 4, that's the square root of 60. 60 is 4 times 15. Why is that important?
Simplification.
Because the square root of 60 then would be the square root of 4, 2, times the square root of 15.
Okay.
So we can simplify that down to that.
Oh, so you just broke it up
Yep.
and then you do the square root. Okay.
Okay, so we'd have, are we done?
No, because
No, why not?
plus and minus. So
Nope.
Oh,
That's not it.
that's a good guess.
What? Nope, that's not it. What variable are we trying to solve for?
X.
X. What variable did we solve for? Y. So what's y equal again?
3 to the X.
3 to the x. So we still have to solve these then, right? Okay. If I try to, if I try to do the one-to-one method, is that going to be realistic?
No.
What power of 3 would give me 4 plus square root 15? Well, does not compute, right? It's actually, you can do it, but you have to use a logarithm to do it anyway. So like, why not just think about this as doing log to both sides?
Can we go over how to do it?
Well, it's kind of stupid, but sure. You're gonna laugh when I show you.
I can't wait.
So x is equal to log base 3 over 4 square root 15. All right, Paul, here's your aside.
Okay.
So we have 3 to the x equals 4 plus square root 15. I'm going to write that as some power of 3.
Oh, sweet.
There you go. Which is exactly what we got when we take the log of base 3 of both sides, right?
That is so fun.
Right? Pretty dumb.
I love that.
Yeah.
Wow.
So that's calculator time now, right?
And then you just cross out the 3's and that's an X. Okay.
Yeah.
I like that.
So when I type that into my calculator, I get about 1.88. I've done this problem like 8 times already, so I just remembered what it was. I didn't feel like typing it into my calculator. You guys are okay with how to do that, though?
Yeah.
If you're not, tell me and we can do it, but I think we are. On the other one, we do the exact same thing, right? We take log base 3 to both sides. When I do that, I get about negative 1.88. So those are my two solutions. What's the one thing I have to be a little bit careful about here? When I write these two exponential equations like this, are they always going to have solutions?
No.
No.
One of them will.
Nope, not necessarily. Why would they not have solutions? What can't we take the log of? Or 0? So if these values were negative or 0, you'd get an error when you tried to take the log of it. In that case, you just have no solution.
You can't do the log of a negative.
Or 0. Yep. It'll give you a domain error on your calculator.
Why wouldn't you be able to take on the negative? Like I understand zero.
Well, so log base b of negative a, equals x implies that b to the x is equal to a negative number. Can I take the power of a positive and get a negative result?
Okay, that makes sense.
Nope.
Right.
So that's why.
I get it.
Everybody cool? Okay. So most of the time, like you can get, your answers are fine. You solve it, the exponential equation, it works, but it doesn't have to, right? If your solutions were to the quadratic were negative or 0.
So wait, real quick. B was negative 3 and x was 1.
B was negative 3. The B can't be negative. Yep. The base of an exponential or a logarithm cannot be negative, or 0, or 1. All right. Let's do some logarithmic equations. So we have 3 times the log of x squared equals 6.
Divided by 3.
Okay. That sounds good to me. Now what?
Can you do
What do you want to do here?
what's the base for this one? Any base? It's not getting to.
Yeah, what's the base for this logarithm here? Does anybody remember? 10 is correct. So one thing you could do is you could do like the exponent base of 10 to both sides. That's okay to think about it that way. Or you could think about this as using the definition of logs to rewrite this as 10 to the second is equal to x squared, right?
Oh, yeah.
Or you could use the 1-to-1 and rewrite 2 as log of 10 squared.
I like that better.
Any of these is fine. They're all doing the same thing.
So what you can do is you can do.
Because what do we get here? We get x squared equals 10 squared, same as we have there. And here you get x squared equals 10 squared. All of them get to the same place, right?
Okay, so if we're doing
Oops. So x is plus or minus the square root of 10. Let's actually write it 10 or negative 10. That'd be easier.
So x is plus or minus.
Everybody cool with that? Well, we square root cancels the squared, right?
Oh, okay. Wait.
Everybody's cool?
Because what you did was you did log base 10 to the other side. But then when
What do you mean, log base 10 to the other side?
well, I don't really fully understand what you did.
Well, I did 3 different things, right? You could do any one of these 3. They're all doing the same thing.
So like for the last one, how are you able to do that?
Use the one-to-one property. It says if I have log of x equal to log of y, then x has to equal y.
Okay, I see.
That's all I used. Does that feel okay? Guess what though?
I just don't see where the other log is. I see log of x squared equals 2.
Mhm.
Is there like an invisible log there?
Well, I rewrote 2 with a logarithm.
Okay, so you were going to the logarithm. So
Yeah.
2 would equal log base 10 squared.
Yeah,
Okay.
because log base 10 is going to cancel exponent base 10, leaving me with 2.
Okay, so log base 10 squared is equal to.
Remember, this was a property that we had. Stupid thing, come on. Right? That was a property that we had way back in section 15.3. That's all I'm using. Right? So 2 would be log 10 of 10 squared. Right? That's all I'm doing.
Is it always going to be log base 10 when you do that?
I mean, it wanted to match the log over here.
Oh, right. Okay, I see.
You know, that's why I use 10.
Okay.
So the 2 logs were the same log. Okay, we're not done though. What do we still have to do?
Find which one's true.
We have to check.
Yeah.
Every logarithmic equation you must check. Why?
Because they can be wrong.
You can get extraneous solutions,
Okay.
right? Now the check is an easy check. All I need to do is take my value, plug it into x in the original equation, and make sure the thing inside the logarithm is positive.
So negative 10 could be the answer because
Yep.
squared.
Yep. So both of them check out. We happy with that? We're on what? E now, right? This will be the last example we'll do today. After this, we'll take the homework quiz and then be done for today. That feels like enough, right?
Yes.
Okay. Oh, no. There's a lot of weird stuff going on in this one too, Mr. Fulak. What do you see that's different about this one?
There are more parts, and it's there's an x minus 1. And
Okay, I have 3 logs, right?
right.
And I have x's in 3 spots.
Yes.
Ew, boy. What should I do first?
We should get everything to one side.
No, I wouldn't do that.
Okay. Can we divide by 2? Oh wait,
I would not divide by 2.
property. Let's add because they all have the same bases, so we can add the 3x minus 2 plus the x plus 1 minus 1.
So what you can do,
It's the power property.
you can do the power property,
That's what I was thinking. Yeah,
but that's not adding,
that's multiplying.
multiplying.
Same thing.
Okay.
Sometimes.
And what can we do over on the other one?
We can subtract it. And
Oh, I'm sorry, not power. This is product.
product. Yeah. We can subtract.
Nope.
No. We can't subtract that.
I mean, you could, but let's not. Power property! That's better. Notice there's a coefficient there, right?
I was thinking subtract and do the power and then do the quotient.
You could do it that way too, but it's kind of yuckier. All right. Now what? You can. I'm going to do that at the same time as I do something else, though.
Well, 2 for 1. 2 birds with 1 stone, as they say. Oh, they cancel out. No, they don't.
Yeah.
Oh,
We use the one-to-one property. Oh, come on. I hate this stupid machine sometimes. I feel like it just wants me to fight it. What's that look like?
Another quadratic.
Quadratic! Great. What do I have to do to solve that?
We have to subtract the x squared. Now we're getting somewhere.
There you go. Got to be equal to 0. To solve this, what can I do?
Can we try foiling first?
We can. It is foiled out.
Can we try reverse foiling first?
You mean factor,
Okay, can we try
or we could use
the
quadratic formula. Now in this case, what's the leading coefficient?
It is 2.
Not 1.
Yeah,
So if I have to factor it, I'm going to have to use that long factor by grouping thing.
Right.
And I'm not even sure at the outset whether it's going to work or not.
I'm not even sure.
I would just use the quadratic formula. It does factor, in case you were curious. But I'm going to use the quadratic formula here.
I thought it might.
Yeah, it will. So negative b plus or minus square root quantity b squared minus 4ac all over 2 times a. So 25 minus 16 is 9. Square root of 9 is 3 over 4. So 5 plus 3 is 8 divided by 4 is 2. And then 5 minus 3 is 2 divided by 4 is 1/2. Then we check. Remember, when we're checking, where are we checking at? The original equation. So all the way back to here. 3 times 2 minus 2. Positive. 2 minus 1.
Positive.
Positive. 2. Positive.
Positive.
That works.
I knew that one. I was just joking.
Oh, come on now. All right. Let's do the 1/2.
It's not positive.
3 times 1/2 minus 2.
Not positive.
Not positive. Come on, you stupid machine. So this is
False.
extraneous.
Extraneous.
It's not one of our solutions.
Not a solution. Correct.
Okay, we're stopping here today. That's good. At this point, you guys could do up to 130. That's going on the problem set for the 8th, though. Fiddlesticks. I forgot to record this. I'm going to give you guys second hour's recording. We did the exact same thing. The only thing that might be different is the questions you asked at the beginning. But the lecture is the same lecture with the same examples. Is that okay? I'm sorry, guys. Mistakes happen. I got too excited.
I got excited. I probably have the same question. I'm gonna go look.
the exponent base and the logarithm can't match. They cancel each other out. Yes.
Oh, so it's like
Tiger. 63,000.
This one's kind of fun.
Yeah, they're all.
it's like this.